All right, so let's talk. This video is going to be about hybridization, bond length, as well as bond strength. Hybridization, focusing on the first two rows, there's two types of bonds. First, there's a sigma bond and a pi bond. Okay, again, this is all review, so we're going to be moving quickly. This is how sigma bonds formed with the overlap head-on, and then the pi bond is with the two parallel p orbitals. And notice, or the point being is that pi bonds don't overlap well, while the sigma bonds do, and so the sigma bonds are much stronger. First row, we have hydrogen. It only has an s orbital, and so here, remember the s orbitals are spherical, and we can have two hydrogen atoms coming together to form a larger molecular orbital like this, and a hydrogen-hydrogen single bond, which is the sigma bond. Okay. For second row, we have both s and p orbitals for bonding. All right, so let's look at carbon, for example, on the second row. Remember the electron configuration for the atomic orbitals is 1s, 2s, 2p, and we've only got 6 valence electrons to fill those. We have to abide by the Aufbau principle, the Hund's rule, etc. So Polyexclusion principle. So valence electrons are used for the bonding, right? That's what we talk about valence electrons being the electrons that dictate the reactivity of an atom, typically. The valence electrons are in the outermost shell, and so those are the ones that are, in carbon's case, in the 2s orbital as well as the 2p. Okay, so this particular electron configuration is in its lowest energy state, which is also known as the ground state. So that's just a vocabulary term for you guys. But these circled electrons are the ones that are the valence electrons, and those are the ones that are dictating the bonding patterns of carbon. And so let's look at methane, for example. We've got carbon with 4 hydrogens on it, and it's 109.5 degrees, and this particular molecule is tetrahedral in its geometry. Okay, so if we were to look at just the s and the p orbitals, remember the s is spherical, and p orbitals are projected in the x, the y, and the z plane. And so those, the way they are, sorry, those are not anywhere close to even. And I like them. They need to be even because remember, these are degenerate orbitals. And so remember, degenerate orbitals are orbitals that are equal in energy or have the same energy. Okay, so back to what I was talking about, which was something chemistry related. So the p orbitals alone wouldn't allow this particular geometry to happen, or tetrahedral, because those are all in the x, y, and z plane, which are 90-degree angles, right? And so molecular orbital theory, we can combine the s and all the p's to make hybrid orbitals, which are sp3 orbitals in this case. And so you combine 4 atomic orbitals, you get 4 hybridized orbitals, and you, in this case, 4 sp3 orbitals. Okay. Now, what you get are 4 degenerate orbitals, and so they're all alike. And so, how does it look different than a typical p orbital? Well, you have the p orbital on the left with the blue and red lobe, and then the p orbital, or the sp3 hybridized orbital on the right. Basically, it just has a larger lobe on one end and a smaller one on the other. And so the blue portion, if you will, is what we're going to draw when we are drawing sp3 orbitals. We're going to avoid drawing this little nubbin on the bottom, the red one, and just to simplify the structures. So that blue portion, again, if you will, is going to be what's used for bonding to create sigma bonds. Okay, so that's boom, 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 boom. We've got those 4 sp3 orbitals projected at 109.5 degree angles because they're all equal in energy, and they want to be as far away from one another as possible, right? Just Vesper theory. So, drawing these four sp3 orbitals, we can also draw how they might bind to a hydrogen atom. So that would just be basically the green spherical s orbital from the hydrogen atom is a 1s orbital. We got 1, 2, 3, 4, and that's more or less the orbitals that are involved in the bonding of between carbon and hydrogen for methane. And we had to combine all of our p orbitals as well as our s orbital to make those four degenerate sp3 hybridized orbitals. So they form four equal sigma bonds at 109.5 degree angles. Okay, and that's hybridization. So this particular carbon is said to be sp3 hybridized because it has four things around it, right? So things could mean atoms or regions of electron density, or just electrons. Okay. All right. So now that we've done the sp3 hybridization, let's take a look at the sp2 hybridized orbitals. So pretty much the same setup, right? So what we want to do, let's take a look at a carbon-containing compound, a hydrocarbon. So two carbons bound to one another with just two hydrogens on each of them and a double bond in between. So you probably remember this structure from general chemistry, and each of these carbons has a 120 degree angle between it, between all of the bonds, and it is at each of the carbons they're said to be trigonal planar. Whoa, trying to take my stuff. All right, so now let's take a look at how we might make these sp2 hybridized orbitals. So we've got our 2s and we've got our 3 2p orbitals, and in order to make an sp2 hybridized orbital, we combine an s orbital and we combine 2 p orbitals. So that's why it's sp2. And that means if we're combining 3 orbitals total, we get 3 degenerate hybridized orbitals, which are sp2 orbitals. We do have that one left over. So that one left over is the vacant, or is the p orbital. That was not combined to make a hybridized orbital. Okay. Now, this is important, and you should remember that forever. Okay, sp2 hybridized orbitals, or sp2 hybridized carbon or atoms have a p orbital that allows it to do things. Okay, now so those sp2 orbitals that are hybridized, or those new hybridized orbitals, those again are making all of the sigma bonds around each of those carbons. So each of these carbons is sp2 hybridized, so I've drawn 3 lobes around them representing the 3 sp2 hybridized orbitals. And they each overlap with either another sp2 orbital for the carbons, that's what makes that sigma bond, or just like in the above structure, we have them overlapping with a 1s orbital for each of those hydrogens. Okay. Now, that's all of the sp2 or and 1s orbitals, but what about that vacant, or what about that p orbital that was left over, right? So the sp2s, they form 3 equal sigma bonds at 120 degree angles. And then, sorry, let me just write this summary down for you. So we've got each sp2 orbital equals a sigma bond, right? And then each 2p orbital is equal to a pi bond. So what does that look like on the structure drawn above? Well, we've got a p orbital that's projected up and down. You can call it the 2pz if you want. And since these are both sticking up and down, they are able to overlap in a parallel fashion. That's how pi bonds are formed, right? So all right, so that overlap is taking place. It's obviously, I mean, this is the best that I could do with my drawing. I think it's quite lovely. So maybe you don't, but drawing it again, it's important to note that once these pi bonds are formed, pi bonds are, if you have a pi bond in between two atoms, that bond cannot rotate. That bond is fixed. And that's because if we were going to rotate that bond, we would have to break the pi bond, and that's going to be way too much energy, so that's not going to happen, at least at room temperature, for example. So it's important to note, again, remember, pi bonds cannot rotate freely or the bond will break. Okay? Sigma bonds, however, like in this guy, methane, those are free to rotate all day long. Okay, because they're overlapping kind of head-on in terms of the lobes of the orbitals. All right, so now we've taken a look at Sp3 and Sp2. Let's take a look at Sp. This is the last one that we really care about in organic chemistry. And we've got our structure here, acetylene. You may know it as the gas we use for acetylene torches. It gets super hot, burns things, melts things, and blinds things. All right, so we've got our setup, the 2s and the 2p. If it's s and p, that means we're only combining an s and p orbital, which means we make 2 sp hybridized orbitals, and then we are left with 2 p orbitals left behind, right? And so if we've got 2 p orbitals left behind, that probably means we're forming 2 pi bonds. Okay, not always, doesn't have to, but it can. And it does in this case. So let's draw out our sp hybridized orbitals. So in this case, they're projected opposite of one another because they want to be as far away from one another as possible. Remember, they're degenerate orbitals, equal in energy in their Vesper theory, right? Get away from me. So sp is the sigma bonds again, like the other hybridized orbitals were in the other structures. 2 sigma bonds, right? And for the p orbitals, oh, I'm sorry, let's do these 1s orbitals so that you can show how the carbons are bound to the hydrogens. All right, and so these 2 p orbitals over here, those are going to be equal to basically the 2 pi bonds that we see in acetylene. So again, 2 p orbitals being left over doesn't mean we have to form those pi bonds, but it does mean we can. And so we did already see the structure had 2 pi bonds, and so what does that look like in the structure that I've drawn? We've got 2 projected up and down, parallel with one another, and then we've got 2 other ones projected in and out of the plane of this computer screen. And so those are also parallel with one another, and so that way they can overlap and kind of form that pi bond, okay? So these 2 carbons are said to be sp hybridized because they have 2 things around them, okay? So there's one region of electron density on one side, and the other side is, it's got that carbon triple bond, and then the other side is a hydrogen. That's another region of electron density, or you can think of it as atoms. This guy right here is sp2 hybridized because he has 3 things around it. And think of it like this. If it's an S and a P with a superscript 2, that's like 2 P's. So S and 2 P's is 3 things. That's 3 atoms that it's bound to. Same thing for this. SP means there's 2 atoms that it's bound to. All right, what's next? Practice. You want to talk about practice? If you don't know what that means, then that makes sense because you're probably way younger than me. But that's Allen Iverson, great basketball player. You can probably Google that if you want, but you might not get it anyway. But I think that's my new thing. Anytime we're doing practice, you want to talk about practice? So 1, let's determine the hybridization of something, and then 2, where do the lone pairs, LPs, reside? Okay, so let's draw out this structure. All right, let's draw it out really fast, actually. All the structures, and then I'll highlight the atoms that we want to determine the hybridization of, and then we can do the lone pairs after. Okay, so what I would encourage you to do anytime we do practice problems is pause the video, try them on your own, and see if you get the same thing I do. Okay, so Let's highlight here. We got this. Boom. All right, cool. So now, top structure. What'd you get? This is what I got. So if we're looking at the oxygen atom that we've highlighted in red, we want to see what the hybridization is of that. And it's got 2 lone pairs around it, so that's 2 things. And it's also bound to a carbon. That's another region of electron density, or another thing. So that's 3 things, which corresponds to Sp2 hybridization. Same thing for this carbon. It's got 1, 2, 3 things around it. That's Sp2 hybridized. So this bottom one is tricky. You may or may not have gotten it right. You have to remember this is a skeletal structure, and that means there's 2 other hydrogens here, which means there's 4 things total on that carbon, as there should always be, or at least 4 bonds, sorry. That's Sp3 hybridized. So this next structure, carbon, CH3, there's 4 things on there. This carbon right here, it's 1 thing right there and on the left side and 1 thing on the other side. That's Sp hybridized. This carbon, got 1, 2, 3 things around it. That's Sp2. This nitrogen, 1, 2, 3. The third thing is a lone pair. That's Sp2 hybridized. Each of these carbons in the bottom structure, we've got, remember, there's 2 hydrogens on that one, plus another, it's bound to a carbon. So that's 3 things, Sp2. The carbon at the center is tricky. There's 2 things that it's bound to, and that makes it Sp hybridized. That's a cool structure. I like that one a lot. Cumulene or aniline. So now what I want to do is look at where do the lone pairs reside, right? So let's look at the top structure again. I've highlighted them in blue, and since that oxygen is Sp2 hybridized and it's already used its vacant or its p orbital to make that pi bond, those lone pairs have to be in the Sp2 hybridized orbital. And the same thing goes for that nitrogen. Since it's already got that pi bond with the p orbital that it didn't form a hybridized bond with, or a hybridized orbital with, then those lone pairs cannot reside in that p orbital. Okay. Here's another example of that where the nitrogen would be Sp2 hybridized and that lone pairs would reside in the Sp2 orbital because that pi bond is already formed. All right, so let's take a look at another practice problem. So we've got a CH3 bound to a carbon, doubly bound to another carbon. So what's the question? So what orbitals make the highlighted sigma bond? Okay. And I've highlighted these ones in red that pertain to this particular question, and then the blue highlight, we'll do that as a separate one, okay? Because that obviously does contain a sigma bond, but we also have the pi bond. So for the red one, these 2 circled atoms are bound together by a Sp3 hybridized orbital and a Sp2 hybridized orbital. These other 2, the carbon and the hydrogen, is a Sp2 and a H1s orbital. Right? Now these blue ones, one of them is a Sp2 bound to a Sp2, while the other is a C2p and a C2p, because that's the pi bond and the other one is the sigma bond. Important to indicate that. Okay, so hopefully that makes sense for you guys. Let me know if you have any questions. All right, so let's move on to bond length and bond strength. So again, reviewing, so it's going to be moving fast. Recall that a sigma bond is stronger than a pi bond. And so this is with respect to bond strength. It's because we have the overlap parallel for the pi and straight up head on for the sigma, and so there's better overlap for the sigma bond. And let's draw out a couple of examples. We got a CC single bond, CC double, and CC triple. Going from left to right, we have an increase in bond strength. Okay, and this makes sense, right? Because it's like you're holding on to something with 3 hands, you're gonna have a tighter hold on it, right? But as we go from right to left, we have an increase in bond length. Again, this inherently it's a kind of intuitive. You have 3 hands on something, you can pull it closer and tighter to your body, right? That's one way to think of it at least. So let's go ahead and write these structures out. what we want to do is kind of take a look at the bond energies and then kind of see why there is a trend, and we want to see why that trend is. So the bond strength in kilojoules per mole for this ethane. So all of the highlighted red bonds are the bonds that the energy that we will be giving. Those two are related. That's what the blue energy corresponds to the red bond. So we've got 368, 635, and 837. So that makes sense that it would take less energy to break a single bond than a triple bond. But notice the triple bond is not 3 times as much energy as the single bond. Now this is a common question in general chemistry because the pi bonds are weaker, so the value associated with breaking that is not the same as a single bond, the sigma bond. Now we look at the CH bonds below. We got 410, 435, and 523. Why are they different at all? Because they're all CH single bonds, right? So why the increase in bond strength for CH? Now take a look closer at the structures of those things. We have Sp3 hybridized carbon versus an Sp2 versus an Sp. So it's all about hybridization. That's what's causing this increase in bond strength. So if we compare an CSPH to a CSP2H and a CSP3H, we can see that the trend as we go from left to right is an increase in bond length. So length. Again, because it's because of the hybridization. And then as we go from right to left, we have an increase in bond strength. So we'll explain why in a second. So it has to do again with the hybridization. So let's tally this up for you. It all has to do with something called S character. So if we take a look, Sp hybridized orbitals, they have one s orbital and one p orbital. Okay. Now that means that 50% of that hybridized orbital has s character, or is s character. So sp2 is hybridized orbital is 1s and then 2p orbitals. That means that 33% of that orbital is s character. And then sp3 hybridized orbital means that we have one s orbital and 3 p orbitals combining to make a hybridized sp3 orbital, and that's 25% s character. So why does this matter? Well, remember that s orbitals are closer to the nucleus, and so this means that the electrons, when they sit in an s orbital, are held more tightly. And so if an orbital has more s character, then that means it's inherently closer to the nucleus, and so the electrons are held more tightly, so it's a stronger, shorter bond. And that's exactly why we see this trend in bond length as well as bond strength. Okay, shorter bonds are stronger bonds. Oh, we want to talk about practice? Let's talk about practice. Okay, so rank in order of increasing bond length. All right, so this long, crazy molecule right here, boom, 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 boom. So we want to rank in order of increasing bond length. Remember, so what I'm going to do is highlight some areas. So this bond here in red, this bond here in blue, this bond here in cool green, and this bond here in pink. I'm also going to number them 1, 2, 3, 4, so we can use the kind of greater than less than sign to indicate our answer. Red, CSP3 bound to a CSP2. Blue, CSP2 bound to a CSP hybridized carbon. And then the green is a CSP bound to a CSP3. The CSP3 bound to a CSP3 for the pink, right? And so, remember, the more S character, the shorter, stronger the bond. So the shorter the bond, the more S character. So since the pink has 2 sp3 hybridized orbitals, that means that it's only 25% s, and it has to be the longest. We write number 4. Okay, it's the longest bond. So now let's take a look at any other sp3, CsP3 hybridized carbons, right? We got 2. Now, what are they bound to? Well, they're bound to, one of them is bound to an sp2 and the other is bound to an sp. So red, which is 1, has to be longer. And then that means 3, which is the other one. And then 2 is the process of elimination. And it makes sense because 2 is an sp hybridized carbon bound to an sp2 hybridized carbon. And that, my friends, is all for today. JK. So, got the joke for you. Who was the spiciest knight at the round table? Sriracha. Ha! Okay, bye.